So let's talk briefly about the trapezoid method. Today is February 29th. I only get to say that once every 4 years. So the whole deal with the trapezoid method is we're typically using it to estimate an integral that you can't do the usual way using the fundamental theorem of calculus. Now we're going to do this for an integral that we can calculate so we can compare the results. So we might say, for example, we want to estimate the integral from, sure, let's make it not terrible, 2 to 6 of the natural log of x using the trapezoid method, trapezoids, I can just say, with n equal to 4. Wow, this is a I've just noticed I put my camera in a slightly different way, and it's really terrible for me. I'm looking here, I'm like, wow, this thing is right in my way of looking. So let me just adjust real quick here because it's really in my way. 1 second. Better. Okay, now I can actually see the paper I'm looking at, which is ideal. All right. So graphically, here's what's going on. We've got our function y equal to the natural log of x, which looks something like this. And from n equals, say, 2, sorry, not n equals, from 2 to 6, we are going to estimate the area under the curve. And we're going to use trapezoids. So let's draw this picture. And so we picked a nice number, usually picking a nice number. So n equals 4, our b minus a over n, which in this case is 6 minus 2 over 4, which is 4 over 4, which is 1, just means each interval has a width of 1. So our intervals are nicely spaced out. It's the interval from 2 to 3, and 3 to 4, and 4 to 5, and 5 to 6. And each of those get a little delta x. So there's your delta x, there's your delta x, etc., etc. And then to do the trapezoid method, we're just going to draw these trapezoids. So here's my first trapezoid. It's like that. My second trapezoid. Drawing it this way, it looks like I'm going to get an underestimate because it looks like all my trapezoids are below my function. And that is actually true in this example. If your curve is concave down, like this one is, any trapezoid will be under the curve, and so you'll have an underestimate. If it had been like an upward opening parabola, any trapezoid would be an overestimate. Who remembers the formula for the area of a trapezoid? I mean, I do because I've done it 1,000 times, but I wouldn't normally. But it's not that bad. The formula for the area of a trapezoid is essentially the average of the heights times the base. So this first trapezoid, and let's write this, yeah. So I would write this formula as T sub 4, T for trapezoid, 4 for the number of intervals, is going to be, how do I want to say this? Yeah, let's just do it this way. So it's going to be delta x, the base of each trapezoid, multiplied by, for each trapezoid, instead of finding essentially, well, we're going to find the height by doing the average of the heights. That's the area of a trapezoid formula. It's the base times the average of the height. So check this out. The first average of heights is going to be f of 2 plus f of 3 divided by 2. That's my first average of heights. My second average of heights is going to be f of 3 plus f of 4 divided by 2. My third average of heights is going to be f of 4 plus f of 5 divided by 2. And my last one is going to be f of 5 plus f of 6 divided by 2. Here's how this shakes out. So watch this for a second. I'm going to factor out the 1/2 from each of these. I'm going to get delta x over 2, which is just 1 over 2, times, now watch this. I have f of 2, and then I have f of 3 plus f of 3, so I have 2 times f of 3. I have 2 times f of 4. I have 2 times f of 5. And I have 1 times f of 6. So this is what I remember about the trapezoid formula. The trapezoid formula is always delta x over 2, and then it's this 1, 2, 2, 2, 2, 2, 2, 2, 2, 2, 2, 2, 2, 2, 2, 2, 2, 1 pattern. The first one and the last one have a coefficient of 1, and all the middle ones have a coefficient of 2. And I'm just using literally every point I've got. So 1 times f of 2 plus 2 times f of 3 plus 2 times f of 4 plus 2 times f of 5 plus 1 times f of 6. And it wouldn't matter if I broke this up into 4 pieces or 40 pieces. It would still be 1 times f of the first one plus 2 times all the middle ones plus 1 times f of the last one. It always works that way. Because every middle one, you're always just doing all these averages of the heights. So in this particular case, that's going to be my delta x is 1. F of 2 is the natural log of 2. F of 3 is the natural log of 3. F of 4 is the natural log of 4. F of 5 is the natural log of 5. Now, the silly part about this is you still have to use a calculator to approximate this. And I always say, if you're using a calculator to approximate your estimate, you might as well just use a calculator to do your estimate in the first place, but that's not the point. Using a calculator, this ends up being approximately 5.34. We've talked a little bit about have we talked about how to integrate natural log of x? I feel like we have. Let's actually calculate the area under the curve just to compare it. So the integral from 2 to 6 of the natural log of x dx, we're just going to do the integral first, and then we'll do the definite integral second. So how do we integrate the natural log of x? What's our method of integration we need to use here? Yeesh, good question. Be careful here. People often make the mistake of saying that the integral of this is 1 over x. That's not true. The derivative of the natural log of x is 1 over x. The antiderivative of the natural log of x is figured out by using integration by parts. I feel like we've done this once already, but we should do it again because I would totally ask this question on a test. I would definitely ask students to integrate natural log of x because it's pretty straightforward once you know how to do it. We're going to let u equal the only thing it could be, the natural log of x. dv has to be the rest, which is kind of the minimal thing dv can be. dv is just going to be dx. And then we fill in the rest of the integration by parts formula. du is the derivative of the natural log of x, which is 1 over x. We multiply by dx. V is the antiderivative of 1 times dx, which is just x. So then this ends up equaling the integral of, oops, sorry, not the integral of, sorry. It's going to be u times v, so x times natural log of x, minus the integral of v du, x times 1 over x dx. And then we should always simplify this integral before trying to deal with it. X times 1 over x is just 1. So the integral of 1 is just x. So we get x times natural log of x minus x. A couple of things I would say about this. I think it's worth memorizing this integral. It's good to know that the integral of the natural log of x is x times the natural log of x minus x. It comes up like just often enough that it's worth memorizing. That said, if someone asks you to do this on a test, they want to see your work. They don't want you to have memorized it and just say, bam, here's the integral. Show the work. You know what the answer is going to be because you memorized it, but you can still show the work to get there. So then my definite integral is going to be equal to x times natural log of x minus x evaluated from 2 to 6. So we're going to get 6 times natural log of 6 minus 6 minus 2 times natural log of 2 minus 2, which ends up being approximately equal to 5.36. So look, our estimate using the trapezoid method is pretty good. Only off by less than 0.02 maybe, or around 0.02. Excuse me. Questions about any of this before we kind of continue on for a little bit? Actually, I have a question for you all. Yeah. Right. So if I was doing, if this was question was asked, if I was given this question where it said, estimate this integral using n equals 4 trapezoids, this would be my final answer. Now I have a question for both of you, and for the people on Zoom as well. Has your instructor talked about the error formulas here? Like how we estimate the error of our approximation? I would love it if the answer was no, because it's not my favorite thing to talk about, to be perfectly frank. That said, if it is something you've talked about in class, we should cover it, and I'm happy to cover it. It's always kind of messy. So for those of you on Zoom, has either Lee or Tavernetti talked about the error formulas, where you've got like some b minus a cubed over 12n squared times the absolute value of the maximum of the second derivative? That's not ringing a bell. Great. That said, and just like with anything, right? If it comes up later, let me know. We can for sure cover it. By the way, just a reminder, this is week 8. We have 2 more weeks of class. We have 4 more class meetings. You all have what, 7 more class meetings? So, right. We still have, and then I still think we still have to talk about like the probability stuff, which is usually the last couple of weeks. I also felt like I needed to mention. Oh, I know this. Just as a side note here, you might have noticed on Canvas at the very top of the modules, there's a survey to fill out. Please do that at some point. I won't know who wrote what. They're anonymous, but I will get all of the comments after the end of the quarter. So I read that, I take that feedback, I try to implement it. If you like, one thing that I did implement because of feedback is I started using pens that were 0.07 instead of 0.05 because someone said, my writing was kind of hard to read. And if you could use a thicker pen, that'd really help. And I think I've made that change for the better. So definitely positive comments. If you have criticisms as well, I'm happy to hear them and try to implement things for the future. All right. I feel like we should do one more example just because the purpose of this really is to estimate the value of an integral that we cannot integrate. So let's look at, that example's terrible. Sure, the standard example. So here is kind of the usual question someone might ask if you're asked to, say, use the trapezoid method. So let's say we want to use the trapezoid, or use the trapezoid rule with, let's change it up and say we have n equal to 5 trapezoids to approximate the integral from, let's make it kind of gross, 0 to 2 e to the negative x squared dx. And the reason this is a typical question is because the integral, or I should say e to the negative x squared, is a function that cannot be anti-differentiated. There is no function whose derivative is equal to e to the negative x squared. That's why it's a prime candidate for this. So the process is still very much the same. And this is why we actually like the trapezoid method better than we like the midpoint rule. Because the trapezoid rule, you just get to use the points that are already like the endpoints of your subintervals. Whereas the midpoint rule, you have to take all your endpoints and then find the midpoint of each of those intervals, which is just more tedious work. So we're going to find our delta x, going to be b minus a over n, which is going to be 2/5. Or if you prefer, you could say it's 0.4. If I was doing this, I would probably write it out on a little number line here. So I would go 0 to 2, and I'm just breaking that up into 5 sections. So I know I'm going to have 2/5, and then 2/5 plus 2/5 is 4/5. 4/5 plus 2/5 is 6/5. 6/5 plus 2/5 is 8/5. I should have picked a different fraction because I'm not great at saying fifths. And then 8/5 plus 2/5 is 10/5, which is 2. So here are my 5 little sections. 1, 2, 3, 4, 5. And again, if you prefer decimals, right? If decimals work nicely, they're totally fine. We could have said 0.4, 0.8, 1.2, 1.6, and 2. That would also work just fine. We're just going to really throw the formula at it, right? The formula, we know the formula here is going to be that our T5 is going to be delta x over 2 times f of the first value plus twice f of the second value plus twice f of the next value plus all the way to twice f of the second to last value, and then finally 1 times f of the last value. So in this particular case, it's going to be delta x, which is 0.4 over 2 times f of 0 plus 2 times f of 2/5 plus 2 times f of 4/5 plus 2 times f of 6/5 plus 2 times f of 8/5 plus 1 times f of 2. It really kind of feels like you're not doing much here, in my opinion. You're kind of just writing down some symbols and then plugging in the right numbers. It is a little bit gross because we're going to have to plug each of these numbers into our function. And our function is e to the negative x squared. So we're going to get 0.4 divided by 2, which is 0.2 times f of 0, which is e to the 0, plus 2 times f of 2/5. Okay. E to the negative 2/5 squared, I'm going to write as e to the negative 4/25. So we get e to the negative 4/25 plus 2 times e to the 4/5 squared is 16/25, so negative 16/25 plus 2 times e to the 6/5 squared is going to be 36/25, so negative 36/25. Finally, 2 times e to the negative 64/25, and lastly, 1 times e to the negative 2 squared is 4. And there's your estimate. And this is how I would leave it. The only thing I might change is that 0.2 is a 1/5 instead of a 0.2, since I kind of was using fractions. But there is your estimate of the area under this curve using n equal to 5 trapezoids. And there's really not anything else we can do here. That's your final answer on a test where you're not using a calculator. Honestly, if I was taking a test, if I was strapped for time, I would be sure to write down that f of x was equal to e to the negative x squared, and then I would leave my answer like this. And then if I had time at the end, I would come back and plug in each of those values to my function and write it out. But this, to me, is good enough personally. I mean, it's probably not actually, but like, it's good enough to get most of the credit if your teacher is a partial credit guy in person, which I think both, I don't know about Lee. I don't know how partial credit Lee is. I feel like he might be less hot on the partial credit than, but I'm pretty sure Tavernetti is pretty like, show your work, get all the partial credit you can. Cool. So that's really all there is to say about the trapezoid method, unless we end up coming back around to talking about the error formula. You just delta x over 2 times the 1, 2, 2, 2, 2, 2, 2, 2, 2, 1 pattern. That's the whole shebang. All right. Why are f of 0? Excellent question. I think you came in a little bit late, Megan. But let me go ahead and not to call you out, just I saw your name. Sorry. Because so when we talk about trapezoids, the area of a trapezoid is given by the base, which is delta x, times the average of the heights. So I'm averaging those first two heights. I'm getting f of 2 plus f of 3 over 2. And then for the next one, f of 3 plus f of 4 over 2. The next one, f of 4 plus f of 5 over 2. And the next one, f of 5 plus f of 6 over 2. But then when I bring out the 1/2, and then I'm left with 1 f of 2, 2 f of 3s, 2 f of 4s, 2 f of 5s, and 1 f of 6. So that's kind of the distinguishing feature of the trapezoid rule, is that you have this 1, 2, 2, 2, 1 pattern, where the first and the last thing only get multiplied by 1, and everything in the middle gets multiplied by 2. It's kind of a neat pattern. I know your teacher's not going to talk about it, but there's also something called Simpson's rule, which has a similar kind of pattern where it goes 1, 4, 2, 4, 2, 4, 2, 4, 2, 4, 2, 4, 1. So you have the same sort of symmetry, but it's a little bit different. The Simpson's rule gives you a better estimate of the area under the curve. It's kind of neat. Okay, people had asked if we could do some trig integrals. Let's take a look at that. Trig integrals are hard because I guess I'm not really exactly sure what people mean when they say trig integrals. There's just such a wide variety of trig integrals. So if you have any questions in mind, I'm certainly happy to kind of address them. I have a few examples I can kind of start with, but if anyone in the chat or the two of you in the room, if you have a specific kind of thing you want me to look at or talk about, I'm happy to. Let me start with an example and then we'll kind of go from there. So let's say we have the following integral. So let's do some trig integrals. The integral from, no, not from, just of cosine x over sine cubed x plus sine squared x. Who came up with this? Okay. So when I see an integral with sines and cosines, or secants and tangents, or cosecants and cotangents, one of the things I usually think of first is, can I do a u substitution? So let me ask everybody, in this integral with sine and cosine, is there a good choice for u? And if there is, what might I choose for u? Let me ask even more directly. Would it make more sense to pick u equal to sine or u equal to cosine? Okay, we have one vote for something. Can I ask you to can I ask you to make a guess? If you had to guess, you can just pick one. It's okay to be wrong. Sure, sine. What about, yeah, and why sine? Why am I picking sine? What's the derivative of sine? Do I have a cosine times dx? I for sure do. On the other hand, if I picked cosine for my u, if I pick u equal to cosine, my du would be sine, and I don't have sine times dx. Because even if you factor out the sine from the bottom, it's still not sine times dx, it's 1 over sine. So I'm always trying to make a choice for u. Sorry, I just wrote cosine. If I'm always trying to make a choice for u, so that the du I end up getting is in my integral. And the derivative of sine is cosine of x. The du is cosine of x times dx, and I exactly have that. If you like, and I do like, you can rewrite this as the integral of 1 over sine cubed x plus sine squared x times cosine of x dx. This is a good problem. I like where this problem is going. So then cosine of x is equal to, sorry, cosine of x times dx is equal to du. You should, I know I've said this like 1,000 times, I'm gonna say it 1,000 first time. When you're doing a u sub, you always want to make sure the dx changes into the du before you deal with the rest of it. But now that we've dealt with that, we can see that sine cubed, excuse me, is going to be u cubed, and sine squared is going to be u squared. So we can rewrite this as the integral of 1 over u cubed plus u squared. And now what? Well, I see a rational function whose degree on top is certainly less than the degree on the bottom, and whose denominator factors. I'm looking at some partial fractions here. So I'm going to rewrite this integral as the integral of 1 over u squared times u plus 1. And I'm going to do a partial fraction decomposition because I don't have any other choice. There is no other method that's going to avail itself here. So we're going to write down, okay, I want everybody to take a minute and write down the partial fraction decomposition. The right-hand side should have 3 fractions. A over something, B over something, C over something. Yes, there should be 3 distinct pieces here. And you may end up, people might write things in different orders. So after we write it all down, you may want to change yours to match with what I'm writing, but whatever order you pick is actually fine. Okay, you should have written that u squared is one of the denominators, u to the first is one of the denominators, and u plus 1 is the other denominator. Because if you have something to a higher power, you need every lesser power out of it as well. I would probably pick the order u squared, u, and u plus 1, but it doesn't actually matter which order you write them in. Okay, then we multiply both sides by the common denominator. So we're going to multiply both sides by u squared times u plus 1. The point of this step is that we shouldn't have any denominators after we complete it. So multiplying u squared times u squared, multiplying u squared times u plus 1 by 1 over u squared times u plus 1, we should just get the numerator. On the right-hand side, Multiplying this by that, the u squared should cancel, and you get a times u plus 1. Multiplying this here, the u's cancel. I should say 1, excuse me, of the u's cancel, and you get b times u to the first times u plus 1. And finally, multiplying here, the u plus 1's cancel, and we get c times u squared. And I'm imagining none of your teachers have talked about the nicer way of doing this, where we pick nice values and just plug them in. Maybe Tav has talked about it. I don't imagine Lee has talked about it. They've probably done the thing where you like multiply out the equations and say you have this much u squared and this much u squared and try to set them equal to each other. Does that sound familiar? You can do that, but I'm going to tell you the best way to do this, the easiest way to do this is always picking the nice values of your variable first. And then if you run out, then doing the other thing. So what's one nice value of u? When I say nice value, what do I mean? Right, something that cancels out almost everything. What's one value of u that's going to make most of these go away? Awesome, -1. What's the other one? Yeah, I see it in the chat. What's the other one? Here's a pro tip. The values you're looking for are the values that make your original expression undefined. So u equals -1 would give us division by 0, and u equals 0 would also give us division by 0. So if do u equals -1, I'm going to get 1 equal to a times 0 plus b times 0 plus c times -1 squared. You really don't need to write the terms that are multiplied by 0. So here we're going to get just c equal to 1. For u equal to 0, we're going to get 1 equal to a times 1 plus b times 0 plus c times 0. So a equals 1. And then finally, we need to find the last one. So what we're going to do is we're going to, this is where I go and equate coefficients. So I always pick the highest power of my variable. I'm going to look at u squared. I'm going to say, great. On the left-hand side, I have 0u squared. On the right-hand side, I don't have a times u squared. I would have b times u, which is a b times u squared. And I do have a c times u squared. Or in other words, the coefficient on the left, 0, has to equal the coefficient on the right, which is b plus c. And knowing that c is equal to 1 means that b has to equal -1. Cool. Then that then allows us to rewrite our integral as the integral of 1 over u squared plus -1 over u plus 1 over u plus 1. And I've run out of room, so we'll go to the next page. So for that integral there, the integral of 1 over u squared minus 1 over u plus 1 over u plus 1. These two pieces, the 1 over u and the 1 over u plus 1, I'm thinking are going to be the natural logs. But the 1 over u squared, we should be thinking of as u to the -2. So we're going to get u to the -1 over -1 minus the natural log of the absolute value of u plus the natural log of the absolute value of u plus 1. Good question. How do we know if it's a negative exponent or a natural log? So specifically when it comes to partial fraction decomposition, if you have a 1 over x or a 1 over u or a 1 over x plus 1 or a 1 over u minus 2, or essentially a 1 over a linear function, some mx plus b, that's when it's going to be a logarithm. When it's any other power like x squared or x cubed or x plus 1 to the 5th, that's when you want to rewrite it as something to a negative power and just use the anti-power rule. For u to the -1, I can't use the anti-power rule because I end up dividing by 0. But for u to the -2, I can use the anti-power rule. So, and I'll show you another example of this just to kind of make it even more clear. So here, finishing this off, I would rewrite this as -1 over u minus the natural log of the absolute value of u plus the natural log of the absolute value of u plus 1. And then we still have to go back and plug in what our choice for u was. So way back in the beginning, we plugged in u equal to sine of x. So our actual final answer is -1 over sine of x minus the natural log of the absolute value of sine of x plus the natural log of the absolute value of sine of x plus 1. Let's see. Which you could totally rewrite in a couple different ways. You don't need to, but if you're looking at a textbook, the answer might look very different from this because they've simplified it in some strange way. I like this question though. Let's look at an example of just like how do we know what to do if we've got some interesting partial fraction decomposition. So let's say we've done a partial fraction decomposition, and at the end we ended up with the integral of, say, 2 over x cubed plus 1 over x squared plus 1 over x, and then we also had minus 5 over x minus 1 to the fourth plus 2 over x minus 1. So here's what I want to say about this. These ones are the ones that are going to be logs, because those have denominators that are linear functions of x. You have something times x to the first plus or minus a constant. The other ones we want to rewrite so that they're anti-power rules. So I would rewrite this integral as the integral of 2 times x to the negative third plus x to the negative second. I would leave this as 1 over x. I know I could write it as x to the negative 1, but to me it's easier to remember its integral is going to be a logarithm if I write it as 1 over x. Minus 5 times x minus 1 to the negative fourth plus 2 over x minus 1. And then to integrate this, I'm using the anti-power rule on these things with negative powers. So I'm going to get 2x to the negative 2 over negative 2 plus x to the negative 1 over negative 1 plus the natural log of the absolute value of x minus 5 x minus 1 to the negative 3 over negative 3 plus 2 times the natural log of the absolute value of x minus 1 plus c. And then if you felt compelled to, and I kind of do, I would do a little bit of simplifying. 2 divided by negative 2 is negative 1. So I would rewrite this as negative 1 over x squared. This x to the negative 1 over negative 1, I'd write as minus 1 over x plus the natural log of the absolute value of x. Minus 5 over minus 3 is plus 5 thirds. So plus 5 over 3 times x minus 1 cubed plus 2 times the natural log of the absolute value of x minus 1. Again, not super necessary, but is the way I would express my answer. I will point out, I kind of glossed over a mini u substitution here. All right, when I'm integrating x minus 1 to the negative fourth, what I'm kind of thinking of is letting u equal x minus 1, and your du is dx. So integrating x minus 1 to the negative fourth is really like integrating u to the negative fourth, and you're just getting u to the negative third divided by negative 3. So hopefully that kind of clarifies how we know if it's a negative exponent or a logarithm. We're just kind of the ones that have an x to the first in the denominator, that's where you are using the logarithm. Otherwise, it's typically anti-power rule. Cool, good questions. Let's look at some more trig things. Ooh, So I should, yeah. How much have your teachers said about like powers of trig functions? Like, have they talked about the even and odd powers of sine and cosine and the even and odd powers of secant and tangent? Does that sound familiar or not? Okay, let me ask some questions here, and then we'll kind of clarify. So, have your teachers talked about how you integrate, say, for example, cosine squared of x? Is that something that's been covered? Or let me show you how, and then we'll talk about ask. So the way you would integrate this is by using, there's two ways of doing this. I'm not a fan of one of them. The normal is a bad word. The typical way of doing this, the way I've seen this done for years and years and years, is to use a trig identity and say it's equal to the integral of 1 plus cosine of 2 times x over 2. That's the fairly standard way of integrating this. And then you're going to get 1/2 times the integral of 1 plus cosine of 2x dx. The 1/2 hangs out. What's the antiderivative of 1? What's the antiderivative of cosine of some stuff? Is it positive or negative? Oh, it's positive. It's right. So right, the derivative of cosine is negative sine. The antiderivative of cosine is positive sine. So it's going to be almost sine of 2x, except the derivative of sine of 2x would be cosine of 2x times 2. So we have to divide by 2 to account for that eventual change. So the answer here would be 1/2 x plus sine of 2x over 4 plus c. Does that sound or look familiar at all? It's totally fine if the answer is no. Go on Zoom. Familiar? Yay, nay. Everyone's like, I don't know, maybe. Maybe he said it in class once upon a time. This is what I think of when I think of trig integrals. Why do we put it over 2? Excellent question. So it's because this is a trigonometric identity. So there's 2 identities. Well, there's many identities. There's 2 I'm thinking of. The identities I'm thinking of are that cosine squared of x is equal to 1 plus cosine of 2x divided by 2. And I'll talk about where this comes from in a second. And sine squared of x is equal to 1 minus cosine of 2x divided by 2. Both of these formulas actually come from the double angle formula for cosine. I don't think you probably need to know this, but I'm not going to tell you. So this comes from the fact that we can say that cosine of 2x is equal to cosine squared x minus sine squared x. I know it's probably been a while since you've seen this trig identity. And then what we do with this, depending on which one of these I want, for example, if I want to get the cosine squared one, I'm going to replace sine squared with a trig identity for sine squared, which is 1 minus cosine squared. So I'm actually using another trig identity also. I'm using the fact that cosine squared of x plus sine squared of x is equal to 1. Or in this case, sine squared is equal to 1 minus cosine squared. And then I'm going to simplify the right-hand side. Cosine squared x plus cosine squared x is 2 times cosine squared x minus 1, still equals cosine of 2x. And then I'm going to solve for cosine squared. So I'm going to add 1 to both sides. So 1 plus cosine of 2x is equal to 2 times cosine squared of x. And then I'm going to divide both sides by 2. So the 1 plus cosine of 2x divided by 2 is equal to cosine squared of x. And that is where the division by 2 is coming from, or the putting it over 2 is from this process of deriving this trigonometric identity. Do you need to know this? Probably not. Have you been faced with an integral of cosine squared or sine squared in your whole 16B experience so far? I'm actually asking it because I don't know the answer. Like if you had, you'd remember doing this, I feel like. So I feel like the answer is we haven't seen this, which makes you think we probably only need to get to it. So I guess I should go back to whoever asked about trig integrals and say like, is there like, that's the question I'm looking for. Are there trig integrals you have in mind? Also, before I forget, for the people on Zoom, here's the attendance form again, just in case you hadn't filled it out yet. Can we do 13 from 8.5? Good question. I don't have the book on me. But I know I have the book accessible. Let me take a quick, let me grab the book real quick because I know where it is. Yeah, do I know where it is? I do. Sorry, it's hiding from me. 1 second. Yeah, 8.5, sure. Let's see here. Shared with me. Sorry, there's lots of things. I always forget that my internet connection here is less than excellent. Sure, there we go. Okay. One moment. Or I don't have the book here, and I thought I did. If you know what the problem is, you can also just tell me. Yeah, I thought I had the 16. Sorry, the books are hiding from me. Okay, cool. Awesome. Yes. Excellent. Great. This is kind of what I was thinking. The integral of secant squared divided by tangent. Okay. So my problem is I want to make these problems too hard. So this problem, just like with sines and cosines, when I see secants and tangents, I'm trying to make a choice for a u substitution. And typically, you're either going to pick u equal to tangent or u equal to secant. Just like with sines and cosines, you're typically going to pick u equal to sine or u equal to cosine. So here, I'm going to pick u equal to tangent. And the reason is twofold. One, the derivative is exactly secant squared x. Also, tangent is stuck in the denominator, so that's a good reason why I'm picking it as well. On the other hand, u equal to secant would be a terrible choice because the derivative of secant is secant x times tangent x, and I don't have secant times tangent. Although technically you could make it work if you really wanted to, but we don't. We want to make the easier choice. So here, we're going to rewrite this as the integral of secant squared times dx is just du over tangent of x, which is u, which is going to equal the integral of 1 over u du, which is the natural log of the absolute value of u, plus c, which is going to be the natural log of the absolute value of tangent of x, plus c. And that's the whole story. Let's look at some other examples, because I got other examples now. Now that you said that, I'm like, oh yeah, I can come up with some stuff. So let's say we have something, something terrible. Yeah. Yeah. Let's say we have the integral of, well, I'm going to make this really awful just to show you how it can be fixed easily. Let's say we have, oh, maybe it won't be that awful. Cotangent of x times, let's see, I think cosine. Times cosecant cubed of x dx. There's probably the way to make this work with the u equal to cosecant or u equal to cotangent. But I feel like there's an easier thing to do here. If I'm faced with something that looks challenging with trig, a good tactic is to rewrite it in terms of sines and cosines. So let's rewrite this as cotangent being cosine of x over sine of x. And cosecant is 1 over sine. So cosecant cubed is going to be 1 cubed over sine cubed. But we know that 1 cubed is just 1. So we're not going to write 1 cubed. We're going to write 1. And then I would re-express this as cosine of x divided by sine to the 4th of x. And now, to me, it feels like there's an obvious choice for you. I want you all to think about and write down, should we be writing u equal to sine of x or should we be writing u equal to cosine of x? I'll give you 15 seconds to write down your choice of u. Or 20 seconds, because I'm not going to keep in time. If you made your choice for u, you should also write down what du is. Right. Hopefully you've all chosen. I can't see your choice, so it's totally fine if you wrote down the wrong thing. I'm going to pick u equal to sine of x. And the reason I'm picking that mostly is because I know that the derivative is equal to cosine of x. So my du is going to be cosine of x times dx. And I exactly have that. So then I can rewrite my integral as the integral of du on top, and sine of x to the 4th power is going to become u to the 4th power. We should rewrite this as the integral of u to the negative 4th, because it's easier to deal with that way. And the integral of u to the negative 4th is u to the negative 3rd divided by negative 3. Or as I would, plus c, as I would write negative 1/3 times 1 over u cubed, which then becomes negative 1/3 times 1 over sine cubed of x. Which I would probably actually, oh, sorry, plus c, not dx. What am I doing? Holy smokes. Which I would probably rewrite as negative 1/3 times cosecant cubed of x. Let's see. Although you don't have to, it's totally fine to leave it like this. I will point out here. Do I want to point that out? Not really. No, I do. Yeah. Yeah. We could have done this a different way. And I think it's worth mentioning just so you can see that there's more than one way to tackle a problem like this. But I do think the way we've done it here is probably the most straightforward way. Maybe. Here's how we could have done this instead. We could have let u equal cosecant of x. And this is a harder choice, I think, because we're probably less likely to remember what the derivative of cosecant is. The derivative of cosecant is negative cosecant of x times cotangent of x dx. So my integral here, I definitely have a cosecant times cotangent. I don't have the negative sign though, so I'm going to make it a negative du equal to a positive cosecant of x times cotangent of x dx. And then I'm going to rewrite my integral. I'm going to rewrite cotangent of x times cosecant cubed of x as the integral of cosecant squared times cosecant times cotangent times dx, so that I can see the piece that's equal to the du thing. So this part right here, that's equal to negative du. And then the cosecant squared is going to be equal to u squared. So I can rewrite this as the integral of, I should say, the negative integral of u squared du, which becomes negative u to the third over 3 plus c, which is negative cosecant cubed of x all over 3 plus c. Same answer, different way of getting there. Either way is fine. I think so. Yeah. So someone asked, should we rewrite everything in terms of sine and cosine if we are given a problem like this? And I would say, if something else more obvious doesn't immediately seem, if there isn't something else that seems more obvious. So yeah, I think rewriting things in terms of sines and cosines is a good tactic if there isn't a better choice. So I will say we also probably could have done that for this original problem here, but to me it was more obvious that the derivative tangent was secant squared, so we just used that right away. Let's look at, well, let's look at maybe one more example. We got time. So let's say we wanted to find the integral of, I don't love that problem, but we can do it. Let's say we want to find the integral of cosine cubed x sine of x dx. I should ask, in these problems, have your teachers been talking about using a lot of trig identities, like replacing a sine squared with a 1 minus cosine squared? Okay, I don't think so, but I just wanted to double check. That is a thing that gets thrown around a lot with these, but it doesn't have to be. So if I was going to, in fact, I want you all to try this one. So I want you all to try this one, make a choice for you. There's definitely a better choice for you here. Yeah, I'll give you like a minute and a half-ish. All right, let's see where we're at. So even though you could technically make either choice, picking u equal to cosine is the better choice here because you have cosine raised to the third power and you only have sine to the first. So if we pick u equal to cosine, yeah, we're going to have a negative sign. Such is life. Pick u equal to cosine of x. The du is going to be negative sine of x times dx. And we're going to get negative du equal to positive sine of x dx. So I'm going to rewrite this. There's my negative du. And then cosine cubed becomes u cubed. If we made the other choice, if we pick u equal to sine, your du would be cosine x dx, and there'd still be a leftover cosine squared, which is something we could deal with, but it's definitely more work to do it that way. So if you have the choice between picking u equal to sine, u equal to cosine, you typically want to pick the one that's kind of stuck inside some other function. Here, cosine is stuck being raised to the third power. So then we rewrite this. We've got the negative integral of u to the third du, which is going to be negative u to the fourth divided by 4 plus c, which is negative cosine to the fourth x over 4 plus c. And if you're not sure if that's right, you could think about taking the derivative of negative 1/4 times cosine of x to the fourth. And the derivative of negative 1/4 times some stuff to the fourth power is going to be negative 1/4 times 4 times your stuff to the third power times the derivative of your stuff. And oh, look, this derivative is exactly the thing we started off with when we were trying to integrate. The negative 1/4 times 4 times negative 1 is just 1, and you've got cosine cubed times sine. So same thing. I think that's most of, let's do one. Yeah, one more. We can do one more. Sure. Yeah. Let's do the following. We'll do one more trig integral. Sorry, I'm moving out kind of fast. And then we can do some partial fractions. Some more partial fractions. Or was it improper? No, it was partial fractions. Yeah. Not that, I mean, at this stage, kind of everything melds together. Like a problem could have a lot of different things involved in. Like the first problem we did was trig and partial fractions. Let's say we wanted to do the integral of secant to the 5th x times tangent x dx. So you got two choices. You can either pick u equal to tangent or u equal to secant. One of those is the superior choice. One of those is actually not the right choice completely. Like in the previous example, you could have made either choice and would have worked out eventually with some trig identities. Here, there is one right choice and one wrong choice. Letting u equal to tangent is the wrong choice. And here's why. You let u equal to tangent, your du would be secant squared x dx. And yeah, we have a secant squared, but then the remaining secant cubed is very problematic. On the other hand, if we let u equal secant, what's the derivative of secant of x? It's been a while. What is the derivative of secant of x? It is secant of x times tangent of x. And look, I have a secant of x times tangent. I actually have a lot of secants of x, but I certainly have at least one of them. I can rewrite this integral as secant to some power times secant of x times tangent of x. And now it's exactly looking good. This secant of x times tangent of x dx is going to equal my du, and this secant to the fourth is going to equal u to the fourth. So I can rewrite this as the integral of u to the fourth du, which is then going to be u to the 5th over 5 plus c, which is then going to be secant to the 5th of x over 5 plus c. Not too terrible. Oh, I just thought of another one that's worth mentioning. What if you're stuck with something like the integral of secant of 3x? I think this is one that you're expected to just know. I know we mentioned it a while back. The antiderivative of secant of x is the natural log of the absolute value of secant of x plus tangent of x. Does that ring a bell? I feel like we talked about that at some point. You might have forgotten it. It's okay. So we know that the integral, or we have seen at least once, the integral of secant of x is the natural log of the absolute value of secant of x plus tangent of x. The one thing I remember about this really is that the derivative of secant is secant times tangent, and the antiderivative of secant should also have a secant and a tangent. They're just not the same. It's the natural log of secant plus tangent. So if I want to find the antiderivative of secant of 3x, it's going to be almost the same as this. It's going to be the natural log of secant of 3x plus tangent of 3x. And if you had to guess, what do I have to divide by? What seems like the logical choice for what I would have to divide by here? You can type it in the chat. One number. What's the only number that we have that it would even make sense? Right, the 3 is the only plausible choice here for something we'd have to divide by. And that is the choice. Just like if you're integrating cosine of 6x and you get sine of 6x divided by 6 or times 1/6, same idea. The chain rule means we're going to have to divide by the multiple of x there. So there's some trig integrals. They're kind of funky. Most of the time, I would say most of the time with the trig integral, you're often doing a u substitution to solve it. Not 100% of the time, but very frequently. Hopefully that satisfies the need to see trig integrals. I mean, I could go on and on and on and on and on, but let's not. That said, if there are other specific trig integral questions you would like me to address, throw it in the chat or ask me. I'm happy to do them. I don't have, unfortunately, I really thought I had the textbook somewhere on here that was easy to access, but I guess I don't, or I've forgotten where it is. So if you have other questions you would like to see, I'm happy to address them. I just don't have any off the top of my head, really. That's not what I wanted. Sorry. Interesting. Yeah, really. So I'm just annoyed with myself that it's like, I thought it was in here. Let's look at a few more partial fractions problems, because I feel like for people, partial fractions is kind of one of the harder things. Let's look at something kind of gross. Let's look at, say, and I'm gonna make something up which is almost guaranteed to be awful. Sometimes we have awful problems. Let's say we have the integral of 2x plus 1 over, x times x plus 1 cubed. A good sign that we know we're going to have to use partial fractions is that they've already factored the denominator for you. That doesn't always mean you'll have to, or if it's not factored, it doesn't mean you won't have to. But typically, if they've already factored the denominator for you, it's a pretty good place to start with saying, I should probably try partial fractions. You might look for a u sub first. I don't see letting u equal x plus 1 giving us any kind of help here. So let's go ahead, and I want all of you on Zoom, not just the 2 of you in class. I want all of you to write out the partial fraction. Actually, let me ask one question. I want people on Zoom to write their answer in the chat. I want people in class to show me on their fingers. How many fractions are there going to be in my partial fraction decomposition? Good. Yeah. How about people in class? Show me on your fingers. How many fractions does this partial fraction decomposition get to have? Yeah, all your fingers except your thumb. 4 pieces. So you're going to have 2x plus 1 over x plus 1. Sorry, I forgot the x there. X times x plus 1 cubed. You're going to have an a over x, and then a b over x plus 1 cubed, and then every lesser power down to 1. So there's our 4 fractions in our partial fraction decomposition. I'm going to point out that this problem is really more of an algebra challenging problem than an integration. Like the integral at the end of the day is going to be pretty not too terrible. The algebra here, okay, we'll do a different one in a minute here. The algebra here is what's going to be kind of gross. So we're multiplying both sides by our common denominator. So we're going to get on the left-hand side 2x plus 1. On the right-hand side, a times x plus 1 cubed plus b times x plus c times x plus 1 plus d times x squared. Sorry, I'm making a mistake here. Apologies. D times x plus 1 squared. Sorry about that. So the mistake I made there was not actually drawing the thing. If I'd done this times this, I'd be like, oh yeah, the x's cancel. This times this, the x plus cube cancels. This times this, 1 of the x plus, or 2 of the x plus 1s cancel, and I get x plus 1 times x. And here, 1 of the x plus 1 squared times x. So it's always good to kind of think about the work you're doing instead of just assuming you know what you're going to do. As I'm always going to do, and you should always do with the partial fraction decomposition, use your nice values. Use your x equal to -1. Use your x equal to 0. X equal to -1, I'm going to get -2 plus 1 equal to a times 0 plus b times -1 plus c times 0 plus d times 0. I'm going to get -1 equal to -b, so b equals 1. How lovely. I didn't even plan it out, and it came out nice. How great is that? Hopefully it continues that way. For x equal to 0, I'm going to get 0 plus 1 on the left equal to a times 0 plus 1 cubed, so that's a times 1 plus b times 0 plus c times 0 plus d times 0. So I get a equal to 1. Wow. I guess I just had so much practice, I just naturally come up with good problems. How lucky am I? Okay, we've run out of nice values. The terrible thing you can do at this juncture is just pick other values of x. But that's really, really only a good choice if you only have one thing left to find. But I have 2 things left to find, which means I'd actually have to pick 2 different values of x, plug them both in to get a system of equations. It's just terrible. So what we should do here now is start equating coefficients. So let me ask everybody, if you multiply it out either side, what's the highest power of x you would get? Is it 1, 2, 3, 4, or 5? Let's see, if I multiply that x plus 1 cubed, I would get x to the 3rd. If I multiply that, I get x there. Here I get x squared. Here I get x times x squared, which would also be x to the 3rd. So it looks like x to the 3rd is the highest power of x I have on either side. And typically the right side will always have the higher powers than the left side. They could be equal, but the left side will never have a higher power than the right side. So looking at the highest power first, x cubed. On the left-hand side, I have 0x cubed. On the right-hand side, I would have a times 1x cubed. And I'd have b times, I don't have a b times x cubed. I don't have a c times x cubed, but it would have a d times x cubed. So I'm lucky here. I get 0 equal to a plus d, which means d is equal to -a, and a is 1, so d is equal to -1. Cool. Now is where things start to get a little bit dicey. If I look at x squared, I do have 0x squared on the left. How much x squared do I have on the right? It's not pretty. So this is where you might actually have to multiply things out. So looking at this here, we actually multiply the right-hand side. X plus 1 cubed is something you probably actually want to know how to multiply it out. It's going to be x cubed plus 3x squared plus 3x plus 1. C times x plus 1 is c times x squared plus x. And x plus 1 squared is x squared plus 2x plus 1. If you multiply that by x, you get x cubed plus 2x squared plus x. And so just to kind of go back a step, my x cubed thing was right? My x cubed on the left was 0. On the right, I have a times x cubed, and I have d times x cubed. No other x cubed terms. Now for x squared, let's take a look. I would have a times 3x squared, or a 3ax squared. I'd have a c times x squared, and I'd have a d times 2x squared, or a 2dx squared. Or in other words, 0 should equal 3a plus c plus 2d. I know that a equals 1. I know that d equals -1. So 0 equals 3 minus 2 plus c, so c equals -1. I come up with a problem with really nice values. How wonderful. I should write this one down and keep it in my back pocket. Okay, finishing the finishing the partial fraction decomposition is almost never the end of the story. I guess someone could ask you a question on a test where they just said, find the partial fraction decomposition and find the values of a, b, c, and d, and don't actually do the integral. But that's not typical. Usually they're asking you to do the integral. So now, do the integral. We're going to be doing the integral of 2x plus 1 over x times x plus 1 cubed dx is going to equal, so let's just remind ourselves, a and b are both +1, c and d are both -1. That works out great. It's going to be the integral of 1 over x plus 1 over x plus 1 cubed plus -1 over x plus 1 squared. I would normally write minus, but I missed it. And then minus, let's just say plus -1 over x plus 1. The two outer ones are going to be logarithms because, again, the denominator is a linear function of x. The two inner ones are going to be not. So I would rewrite the integral as the integral of 1 over x plus 1 to the -3rd minus x plus 1 to the -2nd minus 1 over x plus 1. And then we're going to integrate, and we're going to get the natural log of the absolute value of x plus x plus 1 to the -2 over -2 minus x plus 1 to the -1 over -1 minus the natural log of the absolute value of x plus 1. If I was taking a test, I'd leave it like that. If I was trying to make it look pretty, I would rewrite it as the natural log of the absolute value of x minus the natural log of the absolute value of x plus 1 minus 1 over 2 times x plus 1 squared minus a minus is plus 1 over x plus 1 plus c. And if you're looking at a textbook and the answer, they'll probably write it as the natural log of the absolute value of x over x plus 1 instead of the natural log of x minus the natural log of x plus 1. It's pretty standard to compress that like that. You shouldn't take the time or the mental energy to do that on an exam. You should stop here. And then if you have time at the end and you feel like it needs to look nicer, you can do more to it. But really, 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 that is not the place where you're getting points on the test. Honestly, it's the place where you're going to accidentally lose points because you might simplify this incorrectly. And someone's like, oh, they had the right answer, but then they messed it up in the next step. So they're going to lose half a point for simplifying it. So don't simplify unless you're really asked to. Most of the time, especially in the Tavern, I'm pretty sure he usually says, do not simplify unless he really, really wants you to. Okay, let's look at one more partial fractions thing and then we'll call it a day. Yeah, I had something in mind. Yeah, let's do that. Let's do something else awful. Sure. Ooh, should we do that? That'd be terrible. That'd be really terrible. No, let's not do that. Let's look at something like, yeah, let's do the following. So the integral of 3x plus 5 over, sure, I'm going to make this kind of hard. Yeah, sure. Over 9x cubed plus 12x squared plus 4x. Well, that was terrible. Okay, so here's the thought process. I don't have a mixture, right? I don't have a log or an exponential or a trig. And when I don't have a mixture, I can't even think about integration by parts. And even if I could, I wouldn't think of that first. I would still look for a u sub first. I don't see a plausible u sub. If I let u equal the denominator, the du would be 27x squared plus 24x plus 4, which I definitely don't have in the numerator. Seeing a rational function and not seeing a good u sub, the next place I go to is, can I use partial fractions? So, can I use partial fractions? Well, only if the denominator factor is full. I should say, I've met all the criteria to use partial fractions except for does the denominator factor, right? I can certainly see that my degree on top is less than the degree on the bottom. I can also see that it's a rational function, but does the denominator factor? Well, I think so. Let's see. I can factor out an x, and I'm left with x times 9x squared plus 12x plus 4. And assuming I've done this right, does this part factor here? Ugh, maybe. So the thing here is you really kind of want to just guess, right? What would we like it to factor? So do I want to have a 9x and a 1x, or do I want to have a 3x and a 3x? I probably prefer a 3x and a 3x. I'd really love it if I didn't have a lot to factor. So it's probably going to be a 3x here and a 3x here. And then it could either be a 1 and a 4 or a 2 and a 2. And it's probably going to be a 2 and a 2. And it is. Because 3x plus 2 times 3x plus 2, the middle term is 6x plus 6x, which is 12x. Oh, but look, that's really, and you definitely should, when you factor the denominator, if you have repeated factors, you should write it as 3x plus 2 squared. I've definitely seen people accidentally in the past, like write it as something over this, and then write it as like a over x plus b over 3x plus 2 plus c over 3x plus 2, because they thought those were different factors. They're not different, they're the same. So then we're going to write this as 3x plus 5 over x times 3x plus 2 squared. And our three fractions in our partial fraction decomposition are going to be a over x plus b over 3x plus 2 squared plus c over 3x plus 2. Some people write these powers in increasing order as opposed to decreasing. It doesn't matter which order you write them in as long as you get all the pieces you need. All right, multiply both sides by the common denominator. So we're going to get the left-hand side, 3x plus 5. Ooh, the numbers are not going to be nice here. Just a warning. On the right-hand side, we're going to get a times 3x plus 2 squared plus b times x plus c times x times 3x plus 2. Okay. What's my easier nice value of x I'm going to plug in? Or my integer non-fractional value of x? I know you know it. What is it? Anybody on Zoom want to chime in here? I know you know. That's the harder one. And I definitely, sorry. So negative 2 over 3 is definitely the harder, less nice value. What's the easy one? It's the one that's also easy to miss. Because I know you're looking for like an x minus 5 and say x equal to 5. Or an x plus 4 and say x equal to negative 4. But you have just a good old x by itself. And if x is by itself, that means x equal to 0 is the other number I want. Another way to look for it is to ask yourself, in this original decomposition, what values of x make the right-hand side undefined? Oh, x equals 0 would make that undefined. That means it's a good choice. But definitely don't sleep on x equal to 0. It's often one of the values that's easy to plug in and find things. So now we're going to get for x equal to 0, on the left-hand side, 5. On the right-hand side, a times 2 squared. Plus b times 0 plus c times 0. So a is going to be the beautiful 5/4. Okay. And then plugging in negative 2/3. Yeesh. Actually, on the left-hand side, it's not too bad. On the left-hand side, you have 3 times negative 2/3 plus 5, which is going to be negative 2 plus 5, which is 3. On the right-hand side, you get a times 0 plus b times negative 2/3 plus c times 0. So here you're going to get negative 2 plus 5. So 3 equals negative 2/3 times b. And to get b, just multiply both sides by the reciprocal. So negative 3/2 times 3 is equal to b. So b is equal to negative 9/2. And once again, we're in the situation where we've ran out of nice values of x. So we're going to start equating coefficients. And here I'm going to look at the highest power of x, which is x squared. On the on the left-hand side, I have 0x squared. On the right-hand side, I would have a times 9x squared. And I'd have c times x times 3x, so I'd have c times 3x squared. Or in other words, 0 equals 9a plus 3c. I'm going to plug in 5/4 for a, so 0 equals 9 times 5/4 plus 3 times c. Subtracting that over, I've got negative 9 times 5/4 equals 3c. Dividing by 3, negative 3 times 5/4 is equal to negative 15/4, which is my c value. Not very lovely, but not unreasonable in the world of partial fractions. So now we're going to go find our integral. It's going to be the integral of a over x, so 5/4 over x. I'm really not even, that constant there, although I do need to know it to get the right answer, is really kind of inconsequential as far as the integral goes. Similarly, I'm going to have a negative 9/2 over 3x plus 2 squared and a negative 15/4 over 3x plus 2. But honestly, when I do my integral here, I'm kind of ignoring those constants. So I know that my answer here is going to be 5/4 times the integral of 1 over x, which is the natural log of the absolute value of x, minus 9/2 times the integral of 3x plus 2 to the, 1 over 3x plus 2 squared, or 3x plus 2 to the negative second. The integral of 3x plus 2 to the negative second is going to be 3x plus 2 to the negative 1 divided by negative 1, and also divided by 3, because of that 3 that's multiplying the x there. So you're going to get 3x plus 2 to the negative 1 divided by negative 1 times 3. And then finally, minus 15/4, and the integral of 1 over 3x plus 2 is the natural log of the absolute value of 3x plus 2, also divided by 3. But those constants just get to kind of hang out in front. And then, yeah, you can make this look prettier, but I don't think we need to. But I'm going to. I would write this as plus 3/2 times 1 over 3x plus 2. This would be minus 5/4, the natural log of absolute value of 3x plus 2. If you really want to simplify your constants, you can, but I wouldn't. All right, that's partial fractions again. They're not too terrible. You just have to be diligent and careful with your work. I mean, that's probably a generally true statement, right? Most of this is not too terrible, but you have to be diligent and careful with your work.